Hello students, in this lecture we will see one important concept related to a vector space, that is the two vector spaces are different but they are structurally same. So we have to define isomorphic vector spaces. Definition: two vector spaces U and phi on the same field F are said to be isomorphic if there exists an linear isomorphism between them, that is a linear transformation T from U to phi which is 1 1 and onto. If U and phi are isomorphic, then we can write, if U and phi are isomorphic, then we can write U is isomorphic to phi by this notation. For example, consider an example M2 by 2R or M2R, simply M2 by 2 or M2R. This is a vector space of all 2 by 2 matrices over R, and this is R4. R4 is the vector space of set of all ordered quadratuples of real numbers. These are the well-known vector spaces. We have to prove that these two vector spaces are isomorphic. Let us see the solution or proof of these two vector spaces are isomorphic. Solution: first, M2R. What is M2R? M2R contains all such that A1, A2, A3, A4 belongs to R, set of real numbers. And R4 is what? R4 is, this is X1, X2, X3, X4. This is set of all ordered quadratuples of real numbers. X1, X2, X3, X4 belongs to R. These two are vector spaces over R. Now we have to define a function. Let us define a map. Let us define a map or a function T from M to R to R4 by T of A1, A2, A3, A4 is equal to a ordered quadruple A1, A2, A3, A4. For all A is equal to, take a matrix A is equal to A1, A2, A3, A4 belongs to M to R. Clearly this T is well defined. Clearly, number one, we have to prove that this T is a linear. First we have to prove that T is well defined, linear, 1 1 and onto. Clearly this linear transformation, that is clearly this T is a transformation. T clearly T is well defined. This is a well defined map. Second one, this T is a linear transformation. When you take A and B two matrices, then T of A plus B, you will get T of A plus T of B by the definition of addition of two quadruples and matrices. Similarly, T of alpha A is equal to alpha into TA. So clearly, obviously this T is again, this T is linear. Or you verify yourself. Then we have to prove that this T is 1 1 and onto. Third one, we have to prove that this T is 1 1. How you can prove that T is 1 1? For that, consider A comma B belongs to M to R. Suppose T of A is equal to T of B. This implies that T of A means what here? This is a 2 by 2 matrix, that is T of A1, A2, A3, A4 equal to T of B is what here? B is equal to, this is a matrix B1, B2, B3, this is B4, belongs to M to R. Therefore this is T of B1, B2, B3 and B4. So this implies that T of A1, A2, A3, A4 is what? This is a quadruple A1, A2, A3, A4 is equal to B1, B2, B3 and B4. So this implies that A1 equal to B1, A2 equal to B2 and A3 equal to B3, and lastly A4 is equal to B4. A is equal to A1, A2, A3, A4. This is equal to B1, B2, B3, B4, the matrix B. So this implies that T is 1 1. T is 1. Now we have to prove that T is a onto. We have to prove that fourth one. T is onto. Fourth one. This T is onto. How you can prove this T is onto? Let x1, x2, x3, x4 belongs to R4 be any vector. Then capital X is equal to x1, x2, x3, x4. This belongs to M to R. This belongs to M to R. Then this is a 2 by 2 matrix over R. Such that how this vector is? Such that T of X is equal to T of x1, x2, x3, x4 is equal to x1 ordered quadruple x2, x3, x4. Okay. So what we have? We have for any vector x1, x2, x3, x4 belongs to R4. Call this vector as a small x. Call or denote this vector by a small x. For any vector small x equal to x1, x2, x3, x4, we have a capital X, that is a matrix 2 by 2 matrix, such that T of this capital X is equal to this small x. So what we have? Thus T is onto from 1, 2 and 3, 4, from 1, 2, 3 and 4. T is a linear isomorphism. Means what? There exists a isomorphism between M to R and R4. Therefore, thus we have this M2R is isomorphic to R4. M2R is isomorphic to R4. So these two vector spaces are isomorphic. Similarly, we can prove that any vector space MnR is isomorphic to R2n. Any vector space MnR is isomorphic to R2n. Thank you, students.